So I wanted to review the definition of energy that we're going to be using for our homework. We did this in class after doing our demos, and so just to state it clearly, energy is simply a number that we discovered in nature. It has the units of newtons times meters, or joules. That's how we summarize that unit. And the way it works is this. Take a system, add up all the ways of storing energy at the beginning of a process, and then let the system do something, add up all the ways of storing energy at the end. And what you'll find is that at the beginning of the process and the end of the process, that energy number doesn't change at all. It's a conserved quantity. So one way that we're going to keep track of how energy works in a system, again, we talked about 4 types of energy in class. And I just want to list these again right now. I know they're in your notes and on the previous page, but I'll just list them here. So EK is kinetic energy. That comes from moving. We have EG, which is gravitational energy. That we get from height. We have elastic energy, which comes from springs. And lastly, we have a form of energy called dissipated. And that is energy that it exists, but we can't get to it. It's lost. This usually happens because of some kind of friction, usually due to friction. And so what we're going to do is just explain how we track energy in systems. So the first goal is to sort of introduce the idea of how do we use an abstract definition like this to begin physics problems. Next, we'll take that beginning and go into solving energy problems with numbers. So the idea here is we can take this definition, we can figure out the energy of a system, and we can actually use that to obtain real physics quantities such as height, speed, compression, distance, forces, etc. And that's what we're going to do here. So we have a situation here with a track. This is supposed to be a spring-launched car that goes all the way around this loop-de-loop and ends up at the end. So our goal here is to set up an equation that allows us to account for where the energy is at the beginning of the system in position A and at the end of the system in position B. So, like this. Certain facts that we need to know. First of all, for there to be kinetic energy in the system, you need the speed to be greater than 0. For there to be gravitational energy, you need a height bigger than 0. And to get elastic energy, you actually need to be physically in contact with the spring. And for dissipated, you'll notice they'll have the word friction in the problem. So one thing we want to note. In number 1, it says, in the situation below, a spring launches a roller coaster cart from rest on a frictionless track into a vertical loop. We assume the system consists of the cart, the earth, the track, and the spring. Notice it says frictionless, and what that means is there will be no E dissipated. And so here's how this works. So at the beginning, we aren't moving. We're on the ground. However, we are in contact with the spring, so we do have some elastic energy. Next, we're up here. Observe. The height of this cart is bigger than 0. It is moving, and again, to be clear, yes, there is a spring in this problem, but at this point here, there is no contact with that spring. So in position B, we have kinetic energy and gravitational energy. So what we're going to do is we're literally going to take this definition, add up the energy at the beginning of the process and at the end, and set them equal like this. So our goal here is to write down the energy equation for the system. That's the first goal. So in this case, that's going to be EE equals E kinetic plus E gravitational. And in subsequent problems, we're actually going to do more with this equation to solve for things like, hey, if I launch a train around this loop, how fast will it be going at the top? Or I launch a train and if it's going at a particular speed, how high up would it be? That kind of a thing. Now, for number 2, it says, let's assume that there's friction between the cart and the track, so that means there is E dissipated at the end. So starting at the beginning, here, once again, there is no speed at the beginning. it is on the ground. So that tells us there's no Eg and no Ek. We are in contact with the spring, and therefore we know that there is an elastic energy right here. Next, we go to the top here at B. It is moving and it has height, and there is friction. However, we're no longer touching the spring, so there's none of that. We do have kinetic energy because we're moving. We do have gravity energy because there's height. And because there's friction, we know we lost a little bit of energy in the process to the tracks. It exists, but we can't exploit that energy and remove it from the tracks and put it back into the train. It's just gone. So we have elastic energy being converted into kinetic and gravitational, and lastly, a little bit of dissipated energy. All right, so that's kind of the first part of what we do with how to use energy. In our next set of videos, actually, you know what? We'll continue this in the next video just to give your brain a little bit of a break. We're not moving into numbers yet. No, better yet, let's do this. I want you to attempt problems 6, 7, and 8, and your warm-up on Monday will consist of one of these 3 problems, or perhaps all 3 of them, as your warm-up, and we'll go over it in class. And what I'm going to do in the next video is I'm going to go ahead and actually start using energy equations to solve specific problems with numbers.